Hello everyone. So today I'm going to be showing you how we can use Total Labs Phoretix 1D image analysis software to analyze a Northern blot. Now, if you've seen my Western blot analysis video using Phoretix 1D, the process is going to be very much the same. However, because we're using a Northern blot here, we're analyzing RNA instead of protein. Now, Phoretix 1D is compatible with phosphor imaged RNA. So if you're using film or a high-end scanner that is compatible with phosphor imaging, you can use images from that, or chemiluminescent based techniques of RNA visualization on a membrane. It all depends on what reagents you've got accessible to you and what kind of scanners you've got available to you, if you've got the capability to capture phosphor images, or if you're using film-based techniques, or if you're using a standard gel doc with chemiluminescent techniques, that'll work fine as well. So I've just grabbed this image off the internet, off a paper that I'll link in the description below. Very good paper that talks about lots of different methods for Northern blotting. And luckily for us, it's got all of the molecular weight information included in it, but I'll also be showing you how we'd add that if it wasn't included in the image and only we knew that from the technical specifications of the marker that we'd used as part of the experiment. Now, the first thing I'm going to bring your attention to is the fact that there are some areas of this image that are saturated, and these are shown up in bright orange here by default within Phoretix 1D. Now, we've obviously got this large area here, which is part of the cropping that I've performed to get this image off the internet, and you can see within my bands for my marker lane, we've got some areas of orange as well, and I'll just zoom in on those. So these areas highlighted in orange are areas where the pixel intensity value has hit the highest most value that it could do, essentially saying that it's gone beyond the limit of detection of the device that you've used to capture the image. Now, this is fine if it's part of your marker lane. If your marker bands are overexposed, that's fine because we're not quantifying those, we're just using those as, in this case, a nucleotide marker. If they were part of my bands for my samples that I was wanting to quantify, that would mean that I can't accurately quantify those bands because essentially the value could be much higher than the value I'm seeing. I've just reached the limit of what I can measure. So if you were to run into that, what the easiest fix would be to expose your membrane for less time, not have an overexposed membrane. To try and bring that down. So that's highlighted by default. So I'll have a look at my image here in the 3D view, and I can see that I'm seeing my bands represented by lovely peaks rather than troughs. So I don't need to invert this image. So I can just go ahead with my analysis. So the first thing I need to do is draw in some lanes. Now, the automatic lane detection algorithm is not going to work on this image because we've got a strong border here, we've got these labels, and obviously the software just assumes we'll see a block or a membrane or a gel rather than seeing text or anything like that. So I'm going to have to do this manually, but Phoretix 1D makes that super easy as well. So first things first, I want to draw a new box in which my lanes will be contained, and I want to draw 5 lanes because there are 5 lanes in this experiment. So if I left click and drag, I create a box with equally sized and equally spaced lanes. Left click to release. Now I can see for the first 3 lanes, all of the bands are contained within the lane, so that's fine. However, for these last 2 lanes, they're slightly warped, they're slightly bent. So what I'm going to need to do is bend my lane boxes to accommodate for that. And that's super easy as well. So if I just click this handle here, I can bend my lane. And what I want to do is as well is just shrink this lane down so I can make sure that I'm capturing only the band information and not this strong border here. And I will bring this lane down as well and move it to match the bend that I've got in my other lane. So it doesn't matter if your lanes are bent as long as your lanes contain the bands that you're wanting to quantify. So as you can see, easy to bend my lanes to match my data and to quantify my data accurately. So if I come down through to the background removal step, if I turn on my different lanes, I can have a look at how my background removal will affect my measurements. Now I'm going to go for trusty rolling ball background removal, and as I change the radius of the ball that I'm using for my background subtraction, you can see how that affects how high the background is coming onto my actual samples. So what we want to do is obviously remove all of this noise, this background here, whilst preserving my bands. So what I just want to do is find a setting that allows me to do that. Yeah, so I'm happy with that. So you can turn all of your lanes on at once to see how it's affecting all of your lanes, or if you just wanted to have one lane on and base your background subtraction just on one lane, you can do that as well. So background subtraction is applied to all lanes equally. However, if I had a multi-channel image, you can change the background subtraction method and intensity per channel. So next I'll come down to assigning my molecular weight ladder. Now, because I've got these values here for my molecular weight ladder, this is nice and easy for me. So these are nucleotides. This is a nucleotide ladder. So what I'm going to do is edit templates, come down to a Northern Blot template that I created. My units are nucleotides. I have 8 steps. There are 8 bands, 8 kind of measurements within this molecular weight ladder, and I've already added these steps in manually to match the steps that are on my image. So if I click save, I select my Northern Blot standard and I left click on the top of my lane here. You can see that I start to get my molecular weight ladder here, and that means I get my measurements when I move through to the band stage. So the next step, and you can change the curve fitting for your molecular weight ladder if you know what it is. If you don't know what it is, if it's not been provided by the manufacturer, the best course of action is to pick the value that has the R squared value closest to 1. What that means is the curve fits the data. The closer to 1 the R squared value, the closer the curve that's been mathematically generated fits the actual data that exists there. So I'm happy with that. It's a really nice curve, and the R squared value is extremely close to 1, so I'm very confident that the mathematically calculated values between my molecular weight ladder markers, my nucleotide markers, sorry, is accurate. So if I come through to my band section now, I'm just going to go for a low intensity default preset. So as you can see, it's picked up some bands, but it's not picked up all of my bands, and it's merged some bands together. But that's easy to correct within the software. So I'll just do this one lane at a time. So if I just show my secondary lane here, I want to probably extend that across there. I want to split this band, right click, split. And then I've got my 3 bands there, and then I've got another band here. So I can just left click and drag to add a new band. And it's all, our software works on data. So you look at the data like this, you look at the raw pixel values and you add your bands to the data rather than to the image. So if I have a look at lane 3, yep, I may want to say that this is a band. Again, this is not the best quality image, it's a PNG that I've just captured off the internet, it's not a TIFF. These values are not the best, however, this is just an example to show you how you would do this. So now we're coming down to lane 4. So this is lane 4 here. Just having a look at these bands here. And again, if I want to change any of the contrast or anything like that to try and make my bands more visible, I can do that within this view as well as the image setup view that we saw before, using things like heat maps, etc. So I'm happy with that, and then lane 5 is somewhat all over the place. So let's have a look across here. This is a very smeared band. It's very difficult even with the data to determine where bands start and end. And I'm going to leave it at that for now, just as an example. If I had any normalization, if I had any standards or a normalization channel or a total protein channel within my image, I could perform normalization here, but I don't, or certainly I don't within this experiment. Quantity calibration, again, I don't have any known standards within this experiment to relate my bands back to calculate quantities or standard curves or anything like that. Annotation, well, if I didn't have this annotation on my image, I could add it manually. Luckily I do, but if I didn't, I would left click and then put in things like 4T here, press enter, 6T here. And if you want to check out more about the annotations mode within Phoretix 1D and what it can do, I've got a separate video on that runs through all of the different options that are on the side here. And then I come down to my results. And I can turn on all of the different values that I want to see as part of my report. Lane name, quantity calibrated volume, etc. Volume here is my peak, where all of my is how many nucleotides are present in my band that I'm looking at. And then I can export all of that information in either a PDF report or a CSV report for onward analysis. As ever, thanks for watching, and if you'd like to try a free copy of Phoretix 1D to analyze Northern blots in your lab, please check out the link in the description below.